Okay, in today's lecture, we're going to cover the first part of the section 3.3 material on Cramer's Rule. So Cramer's Rule is a result which allows us to solve a system of linear equations by making use of determinants. So let's take a look at the statement of Cramer's Rule. So here's what it says. If A is an invertible square matrix, so it has non-zero determinant, then for any vector b in Rn, the unique solution x of the matrix equation Ax equals to b, which would be a representation of a system of linear equations, has entries which are defined as follows. So the ith entry of the solution vector x is defined to be the ratio of the determinant of a matrix A sub I of b divided by the determinant of the coefficient matrix A for that system. Now this matrix A sub I of b is the matrix which is obtained by substituting the vector b, so that is the vector which forms the right-hand side of our equation, for the ith column of the matrix A. So that determinant of the matrix in our numerator for this x sub I coefficient is obtained by looking at the matrix whose ith row is replaced by this vector b on the right-hand side. So Cramer's rule has a proof which isn't particularly difficult, so let's take a look at the proof for this result. So here we will start by denoting the columns of the coefficient matrix A by the vectors A1, A2, up through AN, since this was an n by n matrix. And we're going to denote the columns of the identity matrix, in particular the n by n identity matrix, which is denoted I or I sub n, by E1, E2, up through En. Now, if we're considering the matrix equation, Ax is equal to some vector b, then by the definition of matrix multiplication, we have the following. So if I were to take the product of the coefficient matrix A with the matrix I sub I of x, that is the matrix that I get by replacing the ith row of the identity matrix by the vector x, well, that would be defined as the matrix A times, okay, well, the columns of the identity matrix were denoted as E1, E2, and so on, up through my ith column, which I'm replacing by this vector x, which is the solution that I'm after, and then the remaining columns of the identity matrix up through En. Now the definition of matrix multiplication says, well, this is equivalent to the matrix we get where the first column is the product of the matrix A with the first column of the identity matrix, up through A times the product of the vector x, which would be our ith column of this product, and then A times the nth column of our identity matrix. Now, since A times x is equal to the vector b, we can replace that ith column by the vector b. So we have A times E1 times A, as our first column. The second column would be A times E2 up through, for our ith column, we have A times X, which is equal to B. And then for our nth column, we have A times E sub n. Now, if we're taking the product of a matrix A with one of the columns of the identity matrix, then we have A times E1 would give us just the first column of the matrix A. Up through, for our ith column, we have B, and then for A times E sub n, we would have the nth column of the matrix A. This follows directly from the definition of those column vectors E1, E2, up through En. But now this matrix, which I have here, is the matrix whose columns are the columns of A, A1, A2, up through AN, but where my ith column has been replaced by the vector B. So the notation that we were using for that is A sub I of B. So now if we make use of the multiplicative property of determinants, let's take the determinant on the left and right hand side of our equation. So we would be looking at the determinant of A times I sub I of X, which we know is equal to the product of the determinants. That is the determinant of A times the determinant of capital I sub I of X. And that has to equal to the determinant of the matrix which we had on this right-hand side. So that is the determinant of A sub I of B. But now this determinant of the identity matrix with the ith ith column being replaced by the vector X is just the value of the ith entry of X. So we have the determinant of A times the ith entry of the vector X. We can see that by looking at a cofactor expansion of that matrix along the ith row or column. And this is equal to the determinant of A sub I of B. But now since A, as part of the theorem, was assumed to be invertible, that means that the determinant of A is non-zero, so I can divide through by the determinant of A, and we have X sub I is given by the determinant of A sub I of B over the determinant of the coefficient matrix A. And that was the result that we wanted. Okay, so we've established Cramer's rule, which gives us a technique to solve systems of equations by making use of determinants that we've been working with throughout Chapter 3. So let's look at some examples making use of this theorem. So in our first example, we have a system of two linear equations and two variables. So there's a number of ways we could go about solving this by substitution, expressing it as an augmented matrix, in performing row reduction. But in this example, we're told that we have to use Cramer's rule to find the solution of this linear system. So my first step in applying Cramer's rule would be to introduce some notation. Let's write this system in matrix form, or as a matrix equation. So for this system, our coefficient matrix, capital A, would be the matrix 4, 1, 3, 2. We're taking the coefficients for x1 and x2 in our first and second equations of this system. And the vector B, which would form the right-hand side of the equation, is the vector 6, 7. So this system of equations can be thought of as a matrix equation, AX equals to B, where x is a 2x1 vector of unknowns x1 and x2. Now, Cramer's rule says that we have to find the determinant of this coefficient matrix A in order to find our solution. So the determinant of this 2x2 matrix would be 8 minus 3, which is 5. And then we need the determinant of the matrices A sub 1 of B and A sub 2 of B. So here, A sub 1 of B is the determinant of the matrix we get by replacing the first column of the matrix A by the vector B. So here, recall B was the vector 6, 7. So the first column will be 6, 7. And the second column of the matrix A remains the same, 1, 2. So for our determinant, we have 12 minus 7, which is 5. And then we still need the determinant of A sub 2 of B. That is the matrix that we get by replacing the second column of our coefficient matrix A by the vector B. So here, the determinant of the matrix where the first column is the first column of A, that is 4, 3. And the second column of the matrix A is replaced by B, which was the vector 6, 7. So we have 28 minus 18 for our determinant, which leaves us with 10. So now, by applying Cramer's rule, we have our solution would be given by x1 is equal to the determinant of A sub 1 of B divided by the determinant of A. And using the results we found above, we have 5 divided by 5, or 1. And x2, the second component of our solution vector, would be the determinant of A sub 2 of B divided by the determinant of A. So using our work above, we have 10 over 5, or 2. So we have a unique solution here. The unique solution is the solution 1, 2. All right. So one thing that I'll mention here is, of course, for a system of two equations and two variables, Cramer's rule might not be the easiest approach to solve our system. Maybe row reduction or just direct substitution would be easier here. But for larger systems where row reduction can become quite tedious, this Cramer's rule method is often a bit easier. And one thing to keep in mind in the statement of Cramer's rule, we were assuming that the coefficient matrix A is invertible, so that our solution, or that our equation AX equals B has a unique solution, as guaranteed by the invertible matrix theorem. So this result, Cramer's rule, will not always apply if we have a coefficient matrix A which is not invertible. So that would arise in the case where maybe we have a system with a free variable or infinitely many solutions, so that there's not a unique solution. So when you are trying to apply Cramer's rule to solve a system, I always suggest by looking at that you look at the determinant of the coefficient matrix A first, because if that determinant is 0, that means that A is not invertible and we can't apply Cramer's rule. We would have to use another approach. So let's look at some other examples. In this next example, we have a system of 3 linear equations in 3 variables, x1, x2, x3. And we could solve this a number of ways. But again, we're told in the statement of the problem we have to use Cramer's rule to find our solution. So let's make use of the same approach. We'll start by looking at our coefficient matrix A, which would be the 3 by 3 matrix whose first row is 1, 3, 1. Second row is -1, 0, 2. And our third row is 3, 1, 0. And the vector b, which makes up the right-hand side for our system of equations, would be 4, 2, 2. So we want to solve our system making use of Cramer's rule, which means that we need to calculate several determinants. Here, for a system of 3 equations and 3 variables, we'll need the determinant of A, and then the determinants of 3 other matrices where we replace one of our columns by the vector B. So let's start with the determinant of A. So that is the determinant of our matrix. First row 1, 3, 1, -1, 0, 2, and 3, 1, 0. So using a cofactor expansion, say along our first row, or maybe I could use the second row, we obtain the following. So I'm going to move along my second row since it contains a 0 entry. It'll simplify my work a little bit. So let's determine what the sign of our cofactor expansion will be. So we start with a positive. Then when we move downward to the second row, first column, we get the negative of that entry. So the negative of a -1 gives us a +1 times the minor, which would be the determinant of the matrix 3, 1, 1, 0. Then we have plus our 0 term for the 2, 2 position, and then -2 times the determinant of the matrix 1, 3, 3, 1. So this leaves us with 1 times 0 minus 1, -2 times 1 minus 9. So we have -1, then our -2 times a -8 would be 16. So 16 minus 1 leaves us with 15. Now we also need to find the determinant of the matrix A sub 1 of B. So that would be the determinant of the 3 by 3 matrix where the first column of A is replaced by the vector B, that is 4, 2, 2, and the second column and third column of A remain the same. So again, let's make use of a cofactor expansion to find our determinant. So again, maybe moving along the second row since it contains a 0 entry, we have -2 times the determinant of 3, 1, 1, 0, plus 0, then -2 times the determinant of 4, 3, 2, 1. So this leaves us with -2 times 0 minus 1, -2 times 4 minus 6. So we have a +2 minus our 2 times -2 is a +4. So we're left with 6 here. Now for the determinant of A sub 2 of B, we're taking the determinant of the 3 by 3 matrix where the second column of A is replaced by B. So we have for our first column 1, -1, 3. The second column becomes 4, 2, 2. And our third column is 1, 2, 0. So here we can use a cofactor expansion maybe along the third row or third column, since that would be the only row or column containing a 0 entry. So let me work with the third row here. So let's start by determining our sign. We start with a positive, negative, and then a positive. So we'll have a positive 3 times the determinant of the matrix 4, 1, 2, 2, minus 2 times the determinant of 1, 1, negative 1, 2, and then plus 0 as we're moving along that third row. So this leaves us with 3 times 8 minus 2, minus 2 times 2 minus a negative 1 would be plus 1. So we have 3 times 6 is 18, minus 2 times 3 is 6, which leaves us with 12. All right. So now let's take a look at the determinant of A sub 3 of B. So that is the determinant of the 3 by 3 matrix where our first column is 1, negative 1, 3. Second column is 3, 0, 1. And our third column is now replaced by the vector B, 4, 2, 2. So using a cofactor expansion, maybe along my second row again, since we see that there's a 0 entry there, we would have, for our sign, starting with the positive, then the negative of negative 1. In that second row gives us a positive 1 times the determinant of 3, 4, 1, 2. Plus 0, and then minus 2 times the determinant of 1, 3, 3, 1. So we have 1 times 6 minus 4, minus 2 times 1 minus 9. So that leaves us with 2 minus 2 times our negative 8 would be 16, so 18 for that determinant. So finally, once we've calculated each of these determinants, we're ready to apply Cramer's rule. So by Cramer's rule, we find that the first entry in our solution would be given by the ratio of the determinant of A sub 1 of B, which was 6, divided by the determinant of A, which was 15. So we have 6 over 15, or dividing top and bottom through by 3, 2/5. For x2, the second component of our solution vector, we would be taking the determinant of A2 of B, which we found to be 12, and then divide by the determinant of A, which was 15. So we would have 12 over 15, or dividing through by 3, we have 4/5. And lastly, x3 would be the ratio of the determinant of A3 of B, which was 18, divided by the determinant of A, which was 15. So we have 18 over 15, which reduces to 6/5. So we have, as our solution, the vector 2/5, 4/5, 6/5. Or if we want to think about that as a point which lies on all three of these planes, we've got a point in space given by 2/5, 4/5, 6/5. Now, in this next example, we'll consider a system of linear equations that involves some parameter, A, and we're trying to determine for what values of that parameter a unique solution exists, and then describe our solution set. So this problem, very similar to some of your homework problems. So here we have some parameter we're calling A, and we want the values of that parameter where this system has a unique solution. And then we are supposed to describe the solution in that case. So if we want to make use of Cramer's rule, we could first express this system in matrix form by letting capital A denote our coefficient matrix, which is 3A, 5, 12, and 5A. And the vector B, which forms the right-hand side of our system, is the vector 3, 2. Now we know that this system will have a unique solution if and only if the determinant of A is non-zero. That is, we need A to be invertible. That follows directly from the invertible matrix theorem. A system of the form AX equals to B, where A is a square matrix, has a unique solution if and only if A is invertible, which is equivalent to the determinant of A being equal to 0. So we can say something along the lines of, by the invertible matrix theorem, a unique solution exists if and only if the determinant of A is non-zero. So let's look at the determinant of A. So we would have, for the product of our diagonal entries, 15A squared minus the product of the off diagonals would be 60, and this better not be 0. So here we could divide both sides of our equation or non-equation through by 15, and we would have A squared minus 4 cannot be equal to 0, and so we find A cannot be equal to positive or negative 2. In that case, we would have a matrix which is not invertible, and we would not have a unique solution. We might have an infinite number of solutions if our matrix or our system has a free variable. Provided that A is not equal to plus or minus 2, we have a unique solution. So that was the first part of our problem, is to determine the parameter values where that's true. The second part of the question says to describe our solution in that case. So as long as this determinant is non-zero, we could solve for x1 and x2 by making use of Cramer's rule, which means that we need to find the determinant of the matrices A1 of B and A2 of B. Now for A1 of B, we replace the first column of A by the vector B, which was 3, 2. Then our second column remains the same, 5 and 5A. So we have 15A minus 10 for that determinant. And for the determinant of A2 of B, we're looking at the matrix whose first column is 3A and 12, the first column of A, and our second column is replaced by B, which was the vector 3, 2. So the determinant is then 6A minus 36. So now applying Cramer's rule, we can find the elements of our solution vector, x1 and x2, by taking the ratios of these determinants. So for x1, we're looking at the determinant of A1 of B, which was 15A minus 10, divided by the determinant of A, which was 15A squared minus 60. So we have 15A minus 10 over 15A squared minus 60. And we see, of course, we could divide top and bottom through by 5 and simplify. So if we divide top and bottom through by 5, we have 3A minus 2 and 3A squared minus 4. So as long as A is not equal to plus or minus 2, we have a solution which is defined in the following way. All right. Now, x2, let's see, so we're dividing through by 5. So this last term should not be 4 here. Dividing 60 through by 5, we should have a 12 there. There we go. So 3a minus 2 over 3a squared minus 12 for x1. And then for x2, we're taking the ratio of the determinant of a2 of b, which was 6a minus 36, and then dividing through by the determinant of a, which was again 15a squared minus 60. So we have 6a minus 36 over 15a squared minus 60. Or we could simplify by dividing top and bottom through by 3. So let's see what that leaves us. We would have 2a minus 12 over 5a squared minus 20. So in this first part of our section 3.3 material, we've introduced Cramer's Rule, which gives us a way to solve systems of linear equations by making use of determinants, and we've looked at a few applications.